A really great environment to do fusion is in a plasma. You have hydrogen, and hydrogen is in a very, very excited state. And what happens there is all those hydrogen atoms start to collide with each other. And usually what would happen when it's relatively low energy is the hydrogen will repel each other. But what happens if you get the energy high enough and the hydrogen is high enough, they're going to collide and they're going to fuse. And the nucleuses will fuse. What happens is when you have that fusion, you have a release of a bunch of extra energy, and then that gives off the extra energy you could use for whatever. So you commonly hear that the plasma state is the fourth state of matter. I always kind of push back on that. I always say it's the first state of matter, because when the universe formed, that was the first state. And then as the universe cooled down, if you will, it went from a plasma to a gas to a liquid and eventually to a solid. One of the things I like to use is the analogy of, think of an ice cube, think of water in its solid form. It's ice, you put energy into it, you heat it up, and the water molecules start to melt, and you get a liquid. And then if you put more energy into it, the liquid then goes into steam, into a gas. If you keep putting more energy into a gas, then what will happen is it'll rip apart the molecules, and then you'll also rip out electrons from the atoms and the molecules, and you'll end up with what are called ions, and it makes this soup of charged particles, neutral particles, electrons, positive charge, negative charge, and light. And then at that point there, you've reached a plasma state. It's really easy if you ask nature. I mean, the way that it does it is it does it in stars. So it uses gravitational force, and it creates this huge, huge star. So the sun is 10,000 times larger than the Earth. There's this huge, 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 huge plasma ball. And at the very, very center there, you're getting these fusion reactions because it's extremely hot. The energy, what we call the kinetic energy, the energy of motion happening there, and you get the fusion reaction there. So it's really easy, honestly. What was very difficult is, how do you replicate a star on Earth? Well, you can't work with gravity, because we can't create an object that's larger than the Earth. We can't make us, if we make the sun on Earth, we're going to disintegrate the Earth. So that's not a good approach. So what we need to do is we need to figure out a way to create fusion. And the way we do that is we look, what kind of other forces are there? Well, there's the electromagnetic force. Which one will be useful there? Well, the magnetic force. So what we could do is we can extract a magnetic force, and we can use that to confine a plasma. The only problem there is it's not going to be 15 million Celsius. It's going to be 150 million Celsius. So it's going to be 10 times more energy has to be in that process there. If we can do that, which there's lots of progress in magnetic fusion, for example, happening, then that'll work. The other way we could do it is we use another type of force, which is light force or light pressure. We use laser systems. We very, 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 very precisely aim them at a target that has hydrogen in it. They're all very precisely aimed for a very, very small amount of time. And what happens is fusion. So there's two types of plasmas. So all plasmas are made up of mostly neutral particles, but there's ions, which are charged particles. They can have positive charge, negative charge. So they repel but attract each other, and of course electrons, and then a bunch of photons, or what we'll just call light particles. That's a soup that makes up all plasmas. The difference is, in a hot plasma, they're in equilibrium state. So in the center of a star, or in a star where you have a hot plasma, or an equilibrium plasma as it's called, all of them are at about the same temperature. In a cold plasma, the ions and the neutrals tend to be at room temperature, but the electrons are at a higher temperature. But the electrons, remember, are pieces of those molecules or atoms, right? And they're significantly smaller. They're 10,000 times smaller an electron than an atom would be. And you channel all your energy into the electron. So how do you do that? Well, you use an electric field. And the electric field, or electricity you pass through it, moves those electrons, and those electrons will collide and create ions and create a plasma, but all of the energy is channeled into the electron there. So it's a non-equilibrium plasma, because the high energy, the high kinetic energy is in the electron, but the rest of the stuff can be at room temperature. And we've exploited cold plasmas. I mean, all microchips, pretty much all of civilization, transistors and everything, all semiconductor processed materials are made using cold plasmas. We etch silicon, we deposit on silicon, we put down wires and everything that using cold plasmas, using that type of plasma. So it's technologically what has allowed us to live in the current digital society that we live in. One huge societal problem is of course clean water. The other big societal problem is just food and food production and agriculture. So the way that we do agriculture now is we don't do it at small scale. We do it at very, very, very large scale. We have billions of people to feed, and the problem with that approach is it creates a lot of pollutants, it creates a lot of emissions, it affects our soil, it affects our water systems, it affects, of course, people directly. So there's a lot of issues with that approach. So one of the possibilities with cold plasmas is that instead of making, for example, fertilizer at very large scales, which the way we do that is we have these huge facilities that are equivalent in size to oil refineries, and then we bring that fertilizer to the farms and produce it there. One possibility could be you use cold plasmas to make the fertilizer as needed and on demand as the farmer would need. And of course, each farm is going to have a different quantity that they're going to need, and they can make as much as they need at the moment that they need it, as opposed to just making tons and tons of it and then just storing it or putting it in different places, transporting it, moving it around. All of those things, of course, are what causes the issue. So it's going to allow for a more sustainable farming approach. The other thing with cold plasmas that are very interesting is when they interact with the plants that are food producers, is they seem to stimulate the growth of those plants. When the seeds are treated, they causes the seeds to germinate faster, and when the body of the plants are treated with the cold plasmas, it actually causes them to also increase their yield and grow faster. And of course, if you can grow food faster, that's another advantage. And the reason for that is because if you can grow food in a faster cycle, you can have more cycles of food growth and you can produce more food that way. So there's all of these possibilities that cold plasmas can introduce into agriculture.